This is Trig Identities, part number 17, and I'm going to go ahead and dedicate this to your math gal. The reason for this is I uploaded a video a while back explaining in great detail how the cosine of A equals the negative cosine of A. Now that I've covered René Descartes, which, by the way, René Descartes, even though he came up with x and y, he did not come up with the number lines, nor did he come up with negative numbers. He didn't think anything of negative numbers. Okay? So Euclid had nothing to do with negative numbers. Ptolemy, that Claudius Ptolemy, he had nothing to do with negative numbers. Descartes did not have anything to do with negative numbers. So where in the heck did these negative numbers come from? Well, you have to check out the works of Fermat and Newton to find that. And we will cover that on this YouTube channel sooner or later. Okay? So, there was no concept of negative numbers back in the days when all of this was developed. And I have successfully shown that. Alright. Having said all of that, I now need to prove the law of sines. The reason for that is that there are these addition and subtraction identities in trig, and in order to understand that, you have to have a complete comprehension of Euclid Book 12. It's Euclid Book 2, proposition number 12, and Euclid Book 3, proposition number 20. I covered Euclid Book 2, proposition number 12, which was the law of cosines, back in Trig Identities. If you go through my Trig Identities videos, you'll find that. Now we're going to cover the law of sines. By doing so, you'll have yourself an in-depth understanding of how the addition and subtraction identities actually work, and I will cover that after I cover this. Okay, how do we comprehensively prove the law of sines? We're going to go back to Euclid. We're not going to do it like some of these math teachers. No, we're going to go back to Euclid, and I'm going to show you exactly how it's done. Here's the illustration. We have ABC, which is a triangle. Alright? This is the center of this circle. Okay, we have a circle here. This is the center of it, O. And now we're going to draw two radii. One here, which is OB. One here, which is OC. Now, what is true about all radii of a circle? They're all equal. We proved that in Euclid Book 1. Okay. And then, after we do that, we're going to drop a perpendicular from center O to point P. Okay? And you can do this by Euclid Book 1. As a matter of fact, I'm going to leave that as a homework assignment to you. Find the proof in Euclid Book 1 that says you can drop this perpendicular and bisect this line. It's in there, and you can leave that down in the comments below. I'm going to leave that as for your homework. Alright. Yeah, you're getting homework on this one. Alrighty. Now, what's the first thing we have to do? We have to say that by Euclid Book 3, proposition number 20, BAC, this is BAC right here, or what they would call angle A. Alright? BAC equals BOC divided by 2. Well, what's angle BOC? This is BOC right here. And this angle right here is twice the size of BAC. This is by Euclid Book 3, proposition number 20. Now we can say that BO and CO are equal in size. Why? Because all radii of a circle are equal. We can say that. Alright. We can also say that BPO and CPO are equal because of Euclid Book 3, proposition number 14. Now what is BPO and CPO? BPO is this one, CPO is this one. And by Euclid Book 3, proposition number 14, we can say those things are equal. Alright. Now, we've already established that all radii of a circle, so BO equals CO. We've already established that by bisecting BC, we have BP and PC, and both of those are equal. And we can also say that OP equals itself. What do we have here? We have side, side, side. What's side, side, side? That's Euclid Book 1, proposition number 8. Oh, so these two triangles are equal. Now we get to the meat and potatoes of all this. Alright, since we've said that, Angle BOP equals angle COP. BOP, which is this angle right here, equals COP, which is this angle right here. These two angles are equal. Now, we're going to imagine here, alright? We know that those probably aren't 30-degree angles, but we're going to imagine that these two angles are 30 degrees. Because it'll be a lot easier to explain all this. Alright? So hypothetically, we're going to say that angle BOP is 30 degrees and angle COP is also 30 degrees. Okay, now what happens if you add BOP and COP together? You get 60 degrees. And now we're going to say that angle BOC is 60 degrees. Okay, so if you add angle BOP and COP together, you're going to get BOC. Just that simple. Okay. Now, couldn't we also say that if you add angle BOP and BOP together, in other words, you add two of these, you'll get also 60 degrees? Of course we can. So now we can say that twice of BOP is equal to BOC. We can now say that. So if we take BOC, which is 60 degrees, and we divide it by 2, we get BOP. We can say that. Why is that so important? Okay. Because guess what else we said? At the beginning of the proof, we said that BOC is twice the size of BAC. So if we divide BOC by 2, we get BAC. So that makes BAC equal to BOP. Angle BAC, which is this one right here, is now equal to this one right here. Why is that important? Because we're getting ready to find the sine, okay, of one of these angles. And as soon as we find the sine of one of these angles, that sine will also become that sine. Which angle are we going to find the sine of? Well, now I'm going to tell you. Alright, we can now say that the sine of BC, that's line BC by the way, is equal to the sine of BC is equal to the sine of angle BOP. That's a fact. Now what did we just say? Angle BOP is the same size as angle BAC. So why don't we replace that? I think it's a good idea. Okay. Now we have the sine of BC equaling the sine of BAC. Okay. Now, what is the sine of BOP? Well, the sine of BOP is BP over BO. Okay? The sine of BOP, which is this one right here, is BP over BO. It's the side opposite over the hypotenuse. Well then, couldn't we replace that BP right there? Yes, we can. Let's replace BP with another value. What is BP? Well, I'm going to tell you. Well, BP is half of BC. So couldn't we also say that BC divided by 2 equals BO? Couldn't we say that BC divided by 2, then divided by BO is sine of BOP? Of course we can. But this looks kind of ugly. Let's correct some of this. What are we going to do? We're going to multiply the top and the bottom of this fraction by 2 to get rid of that 2. Okay? Now we can say that BC, right here, BC, divided by twice the size of BO equals the sine of BOP. Now what is BO? Can we replace BO? Absolutely. You know what BO is? That's the radius of a circle. So why don't we replace BO with an R? I think it's a great idea. Now we can say that the sine of BOP is BC over 2R. But there's something else in this equation we can replace. Can you think of what it is? I knew you could think of it. You're right. It's BAC. We said that BOP is equal to BAC. Now we're going to replace that BOP. Is that looking a little more familiar to you now? Should be. But we'll get more familiar in just a second. Now, what's the problem with all this? It's just not in the right configuration yet. We need to fix a few things. We're going to multiply both sides of this equation by 2R. Let's do it. Whoops. I know it's a lot of writing. Okay. Does that look a little more familiar to you? If not, I'm going to show you how it gets to be more familiar. We're now going to divide both sides of this equation by the sine of BAC. Does that look a little more familiar to you? It should, because that is actually 1/3 of the law of sines. It really is. Well, you say, well, what about the other 2/3? How are we going to do all that? Glad you asked. Bear with me. Just got to make a couple slight adjustments. See, we're already starting to make some adjustments. Hold on. I know this isn't a perfect drawing, but I think it'll work. There you go. Then you say, well, that looks a little different. Not really. That look a little better to you? I think so. Okay. Now we're going to do this just a little bit faster because this is almost identical to what we just did. Okay. We now know that angle ACB, this is angle ACB right here, is equal to AOB divided by 2 because AOB is twice the size of ACB. We know that. Okay. We now know that AO and BO are identical in size. How do we know that AO and BO are identical in size? Because all radii of a circle are equal. Okay. Now, we already said that ACB is half the size of AOB, and that's by Euclid Book 3, proposition number 20. We also said that by Euclid Book 4, proposition number 5, AO and BO are the same size. Now, angle APO and BPO are the same size. Angle APO and BPO, they're the same size, and this is by Euclid Book 3, proposition number 14. Now, we've already said these two sides are equal because already I have a circle are equal. OP is equal to itself. We know that. We've already dropped a perpendicular like this, and we bisected this line, so that makes AP and BP exactly the same size. Now we got side, 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 which is equal to Book 1, proposition number 8. That makes AP and BP equal. Alright. Now, we already know that angle AOP and BOP are exactly the same size. AOP and BOP are exactly the same size. We know that because these are two equally sized triangles. Okay. Now, if you add AOP and BOP together, you're going to get AOB. AOP, BOP. Add these two together, you get AOB. We know that. Now, we can say that twice the size of AOP is AOB. We can say that now. Alright. Now, alright here. We've already established the AOP is this right here. We've already established that AOP is AOB divided by 2. Okay? Now, can we replace that AOP? Absolutely. That's yes, it's ACB. Okay? Because AOB is twice the size of ACB. Okay, so now we can say that Okay. Now, we can now say that AOP equals ACB. We can say that. We know that now. All right. Now we just get into a little arithmetic. What are we going to do next? Well, we're going to find the sine of AB. What is the sine of AB? Well, it's equal to the sine of AB is equal to the sine of AOP. Okay. Now, what is the sine of AOP? Well, the sine of AOP is AP over AO. The sine of AOP is the opposite over the hypotenuse. AP being the opposite, AO being the hypotenuse. Okay. Now, can we replace that AP? Think about it. Of course we can. Because what is AP? AP is actually AB divided by 2. Now, can we replace that AO? Of course we can. What is AO? It's the radius of a circle. So let's get rid of AO. Now, can we simplify this fraction? Of course we can. Ta-da! We already did it. Okay. Now, since we know that the sine of AOP is 2r, didn't we say earlier that AOP is the same size as ACB? Of course we did. Well, let's replace that AOP with ACB. Does that look familiar to you? Okay. Now then, Let's take the 2r and multiply it out. Is that looking a little more familiar to you? I bet it is. Okay. So, now what we can do is go 2r and we can do this. That is 2/3 of the law of sines. Now you say, do we have to go through all that mess again to prove the third part? Nope, not at all. We're going to do something immensely clever. We're going to take the mathematics of the textbooks to prove the remaining piece. And the reason for that is it's just a little less time consuming. Okay? And I don't like time consuming things. Okay. Let's go through the last part, shall we? This one won't be so bad. Now, what is the sine of angle ABD? Hang on. Oops. I know this has been a long video, and I'm glad you all bared with me on this. Okay? That's the sine of angle ABD. Okay? Now then, what are we going to do? Well, what we're going to do is actually we should have said this. Okay, now we have AB times the sine of ABC Okay, now we have this. Okay, because remember, all we did was we multiplied both sides of the equation by AB. Okay, now we got this. Now then, what about the sine of angle ACB? What is the sine of angle ACB? What is it equal to? Well, it's equal to that's what it's equal to. Okay, now we're going to multiply both sides of the equation by AC. See, we're going to multiply both sides times AC. And what we're going to get is this. That's what we're going to get. Okay. Now then, Alright, so now we're going to say that BD equals we're also going to say, well, hang on, I'll show this to you. We've now established that BD equals this and BD equals this. Well, by the transitive property, if A equals B and B equals C, then A must equal C. Now we can say something here. Are you ready for this? Looky there. Now then, what's the first thing we're going to do? We're going to divide both sides of this equation by the sine of ACB. So now, there it is. They say that still doesn't look quite right. You're absolutely right. Now we're going to divide both sides of this equation by the sine of ABC. Okay. Does that look a little better? I bet it does. Okay, there's just one final step. Alright. Didn't we say earlier that this one right here equal 2R? Of course we did. If this equals that and this equals this, then 2R equals that. Now you have your law of sines. All of this done without negative numbers. Do you understand? Do you comprehend now why Euclid is so important? Now you get it. This is a lot easier than trying to go through what some of these, I kid you not, I talk to these teachers all the time. There are some teachers out there that just rely nothing but on a modern day textbook. This gives you a greater in-depth understanding of what's going on out there. and I was glad to do this presentation just for you. I know this took a long time, but now I can finish all the trig identities, and we can finally get on our way to learning calculus. I will tell you more in a future video. Stay tuned.